Hello and welcome to Science for Bedtime. If your day has been a little too fast, or your thoughts are still moving ahead of you, you're in the right place. This channel is made for slow science, gentle curiosity, and nights that end softly. And if these calm journeys help you unwind, feel free to subscribe. It's a quiet way to support the channel, and it helps more bedtime listeners find their way here too. Now settle in and let your breathing become easy and unforced. You don't have to concentrate, you don't have to remember anything. You can simply listen and let the ideas pass through like a warm, quiet current. Tonight, we're going to drift into one of the most soothing mysteries in all of mathematics, a pattern that keeps appearing in the natural world like a signature written in spirals and petals and quiet curves. It's called the Fibonacci sequence. And the beautiful thing about it is how simple it begins, like a small step taken in the dark that becomes, slowly, a path. Think of the world when it grows, when it expands, when it repeats itself with variation, when it tries to fill space without wasting energy. You can see that kind of growth in a leaf that turns toward light, in a pine cone that stacks its scales, in a sunflower that arranges its seeds, in a shell that widens without losing its shape. And somehow, again and again, the same gentle numerical rhythm shows up, not perfectly, not rigidly, but close enough to feel like a quiet rule the world often prefers. So tonight, we'll explain the Fibonacci sequence in the most relaxed way possible. We'll move slowly. We'll let examples appear naturally. We'll connect the numbers to spirals, to the golden ratio, to plant growth, to packing problems, to patterns that feel almost like nature's handwriting. And if you find yourself drifting off, that's perfect. That means the story is doing its job. Because this isn't a test, it's a soft walk through a landscape of ideas where even the math can feel like a lullaby. Let's begin with the simplest version of the sequence, the way it starts with almost nothing. The Fibonacci sequence begins with two ones, 1, 1, and after that, each new number is made by adding the two numbers that came before. So 1 plus 1 makes 2, then 1 plus 2 makes 3, then 2 plus 3 makes 5, then 3 plus 5 makes 8, then 5 plus 8 makes 13. And it continues quietly, steadily, like footsteps that keep a rhythm without needing effort. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. It's a simple rule, and yet it creates a sequence that grows in a way that feels natural, not explosive, not linear, but gently accelerating, as if it is always remembering where it came from. And that idea that each new step contains the last two steps is part of what makes it feel so organic, like growth itself. In nature, growth is rarely independent. A leaf is shaped by the stem it attaches to. A branch is shaped by the trunk that supports it. A season is shaped by the one before it. Life builds forward using what already exists, and the Fibonacci sequence has that same feeling, like a memory carried inside the next moment. Now at first, Fibonacci numbers can look like a neat little list, a mathematical toy, something you could write on a napkin and forget. But they have a strange habit of reappearing when you look at how living things arrange themselves in space, especially when they are trying to grow efficiently, or pack densely, or spread without overlapping too much. And to understand why, we can think about a quiet, practical problem that nature constantly faces. How do you place new growth again and again around a center without blocking what came before? How do you add leaves around a stem so they don't all stack in the same shadow? How do you place seeds in a flower head so each seed has room and the whole surface is filled smoothly? How do you keep expanding a shell without changing its shape so the animal inside can grow without losing protection? These are not questions nature asks with words, of course. They're problems solved by evolution and physics and chemistry through millions of small adjustments over time. but the solutions that survive tend to be the ones that waste the least energy and space, and that create forms that are stable, functional, and repeatable. And that's where spiral patterns begin to appear, because spirals are one of the most efficient ways to grow outward while keeping balance, keeping proportion, keeping continuity. A spiral lets you expand without sudden corners. A spiral lets you keep the same shape as you get bigger. A spiral lets you place things around a center without leaving empty gaps. And when spirals emerge from repeated growth, Fibonacci numbers often appear as the counts of spirals in one direction and in the other, like two quiet families of curves weaving past each other. But before we go there, it helps to meet one of Fibonacci's closest companions, a number that is often described as nature's favorite proportion, not because it is magical, but because it shows up naturally when growth follows this kind of self-building rhythm: the golden ratio. The golden ratio is usually written with the Greek letter phi, and its value is about 1.6180339. It is an irrational number, which means it never ends and never repeats, like a decimal that keeps going forever. A river you can't reach the end of, but the way it appears is simple to describe. It emerges when a whole is divided into two parts, so that the ratio of the whole to the larger part is the same as the ratio of the larger part to the smaller part. It's a balance of relationships, a proportion that keeps echoing itself. And here's the gentle link to Fibonacci. If you take Fibonacci numbers and divide one by the one before it, those ratios begin to settle down toward the golden ratio. For example, 13 divided by 8 is 1.625, 21 divided by 13 is about 1.615, 34 divided by 21 is about 1.619, and as you go farther, the ratio gets closer and closer to 1.618, like a moving target that you can approach forever. This is one reason Fibonacci and the golden ratio are so often mentioned together, because the sequence naturally generates ratios that lean toward that proportion, the same way growth processes can lean toward stable solutions. Now, none of this requires believing in perfection. Nature is not a geometry textbook. A sunflower is not trying to follow a formula. A shell is not calculating phi. But when certain growth rules repeat, and certain constraints apply, and certain shapes happen to work well, you can end up with structures that approximate these patterns, not perfectly, but consistently, like a theme in music that keeps returning in different keys. And that's the mood we're going to stay in tonight. We'll treat Fibonacci as a quiet theme, a pattern that helps explain why some things look the way they do, why some forms feel balanced, why certain spirals keep appearing, and why a simple rule can echo outward into so many places, from a plant stem to a storm system to the curve of a galaxy. And we'll do it slowly so your mind can rest while the ideas gently unfold. Let's take one of the most calming and familiar examples: the way leaves arrange themselves around a stem. If you've ever looked at a plant from above, or watched a vine climb, or noticed how a succulent stacks its leaves in a rosette, you may have seen it without realizing it. There's often a spiral, a quiet turn, leaf to leaf, as each new leaf appears slightly rotated from the last. This arrangement is called phyllotaxis, which simply means the way leaves are placed on a plant. And it turns out that one of the most common and efficient arrangements uses an angle that is very close to a special value connected to the golden ratio, called the golden angle. The golden angle is about 137.5 degrees, and it comes from taking a full circle, 360 degrees, and dividing it in a way related to phi, so the spacing avoids simple, repeating overlaps. Here's the calm intuition behind it. If you place each new leaf at an angle that is a simple fraction of a circle, like 180 degrees, you end up with leaves in two neat rows, often shading each other. If you place each new leaf at 120 degrees, you get 3 rows. If you place each new leaf at 90 degrees, you get 4 rows. These patterns repeat too neatly, and neat repetition can cause crowding and shadowing. But if the angle is irrational in a way that does not line up into simple repeating rows, the leaves distribute themselves around the stem more evenly over time. They spread. They avoid stacking in the same line. They make sure more leaves get access to light and air. And that's exactly what the golden angle does. It's not perfect because nature is trying to be artistic. It's effective because it spreads new growth into the gaps again and again, like a careful gardener who never plants the next seed directly on top of the last one. And when you look at those spirals of leaves, you can often count visible spiral lines in 2 directions. And those counts frequently land on Fibonacci numbers like 5 and 8, or 8 and 13, or 13 and 21, depending on the plant and its size and stage of growth. It's one of those moments where math stops feeling like a human invention and starts feeling like a way of describing what growth tends to do when it repeats under constraints, quietly, patiently, beautifully. If you like, you can imagine this as a slow dance of placement, each new leaf arriving with no rush, turning just enough to find a clear space, making room for itself without stealing too much from what came before. And in that sense, Fibonacci is not a strict recipe. It's a description of a habit, the habit of building forward while honoring the past, the habit of filling space without wasting it, the habit of growing in a way that stays balanced, even as it expands. And from here, we can drift naturally into seed packing, because if leaves are one kind of placement problem, seeds are another, and nature solves it with the same calm logic, arranging hundreds or thousands of seeds in a flower head with almost no wasted space, like a living demonstration of efficient geometry made gentle by time. Seed packing is one of the quietest places where Fibonacci begins to feel almost visible, because here the plant is doing something very practical, again and again, without thinking about it in any human way. It's placing new seeds into a limited space, and it wants to fit as many as it can, while keeping the spacing as even as possible, so each seed has room to develop, and the surface gets filled smoothly, without clumps and without wide, empty gaps. This is the same kind of problem you'd face if you tried to place coins in a circle so they look evenly distributed, except the plant is doing it with living growth, expanding outward as it keeps placing new points, one at a time. And when that placement follows an angle close to the golden angle, each new seed tends to land in a gap between earlier seeds rather than lining up with them. And over time, this creates a pattern that looks like 2 families of spirals, curving in opposite directions across the flower head. If you look at a sunflower closely, you can often count these spirals, and you'll find numbers like 34 spirals in one direction and 55 in the other, or 55 and 89, depending on the size of the sunflower and how tightly packed it is. These aren't decorations, they're side effects of a rule that spreads points evenly across a growing disc, and the Fibonacci numbers appear because the geometry naturally organizes into these interlocking spiral counts when the angle is near that golden value. It's calm to imagine, really, like the plant is placing each new seed gently into the next available pocket of space, guided by a quiet, rotational rhythm that keeps balancing itself as it expands. Pine cones and pineapples echo the same idea, except instead of seeds on a disc, you're seeing scales or segments on a 3-dimensional surface, stacked in a way that keeps the structure stable and the packing efficient. On a pine cone, you can trace spiral rows that wrap upward in both directions, and those spiral counts often land on pairs of Fibonacci numbers, like 8 and 13, or 13 and 21, depending on the species and the size. This doesn't mean the cone knows Fibonacci. It means that when growth points are added sequentially with a spacing that avoids repeated overlap, the structure that emerges often organizes into these spiral families, because that's one of the most efficient ways to distribute repeated units on a curved surface without leaving awkward gaps. And it's worth holding on to this idea gently because it helps keep the story grounded. Fibonacci in nature is not usually about perfect matching. It's about repeated growth under constraints, producing patterns that are close enough to the Fibonacci story that the same numbers keep showing up, like a familiar melody returning in different rooms. So when people say sunflowers are Fibonacci, what they really mean is that the plant's growth method often produces spiral counts that fall near consecutive Fibonacci numbers, because that arrangement packs efficiently as the head expands, and because the golden angle style spacing prevents the seeds from lining up into wasteful rows. And once you've seen that, you start noticing a broader theme. Fibonacci appears most often in places where something is being added step by step, each new piece positioned in relation to the recent past, and where the system benefits from even distribution, stable growth, and minimal waste. It's a pattern that loves gradual expansion, the kind of expansion that keeps its balance. It's the same reason spirals keep appearing, because spirals are what you get when you keep moving forward while turning slightly, again and again, letting growth unfold without sudden corners and without forcing a restart. Now, if seeds and leaves show Fibonacci through placement, shells show it through shape, through the way an organism can grow continuously without losing its overall form. Many shells grow in what's called a logarithmic spiral, a curve that keeps the same shape as it expands, simply scaling outward. This is deeply practical. If a shell had to change its design every time the animal grew, it would be fragile and inefficient, but a similar spiral allows the shell to enlarge steadily while keeping the same protective geometry, like a home that gets bigger without needing a redesign. And while the shell's spiral is not always a Fibonacci spiral in a strict mathematical sense, it often looks similar to the spirals we draw from Fibonacci rectangles, because both are part of the same family of expanding curves where growth preserves proportion. This is one reason the Nautilus shell gets mentioned so often in popular explanations, even though real Nautilus shells can vary and don't perfectly match the golden spiral diagram people like to print in textbooks. The deeper point is calmer and more reliable. Spirals that preserve shape during growth are very useful in nature, and Fibonacci is one of the simplest doorways into understanding why such spirals feel so common and so natural. And if we lift our eyes from plants and shells for a moment, spirals appear again in places that aren't alive at all, but still follow similar constraints. Hurricanes form spiraling bands because rotating fluids under pressure, differences naturally create curved flows organized by the Coriolis effect and by the way air and moisture move toward a low-pressure center. Galaxies form spiral arms through gravity and rotation, patterns that unfold over immense time scales, with stars and gas tracing sweeping curves that feel like echoes of smaller spirals on Earth. These spirals are not Fibonacci because Fibonacci, and they're not proof of a single magical number controlling the universe. They're a reminder of something quieter. Spirals are a stable and efficient pattern for systems that rotate and expand, and once you start noticing spirals, you realize nature repeats shapes across wildly different scales because the same kinds of constraints can produce the same kinds of forms. That's one of the most soothing ideas in science, that different worlds can rhyme. Now, before we go deeper into the golden ratio, it helps to return to the Fibonacci sequence itself and see why it naturally connects to growth and proportion in the first place, because the sequence isn't only a list of numbers, it's a rule for building the next step out of the recent past. And when you do that long enough, a certain balance begins to appear, a stable relationship between successive terms. As we mentioned earlier, the ratio of consecutive Fibonacci numbers approaches the golden ratio, like 89/55, 144/89, 233 over 144, each one a little closer to that 1.618 value. This happens because the sequence carries a kind of internal momentum where each new term is made from the last two, so the ratio gradually settles into a steady state, the way a swinging pendulum settles into a rhythm. This is one of the calm ways to understand why F appears so often in discussions of Fibonacci, because F isn't added as decoration. It emerges from the sequence's own structure as a natural limit of its ratios. And once you have a stable ratio, you have a stable way to scale, and stable scaling is exactly what growth often wants, whether it's a shell preserving its shape or a plant distributing leaves evenly as the stem stretches upward. There's also a gentle historical story that often introduces Fibonacci to people for the first time, and it's okay to hold it loosely as a doorway rather than a definition. In the 13th century, Leonardo of Pisa, known as Fibonacci, described a problem about rabbits, imagining pairs of rabbits that reproduce in a simplified pattern, where each new pair is produced by an older pair, month after month, with a delay before newborns can reproduce themselves. The details of the rabbit story aren't biologically realistic, and they don't need to be, because the point is not rabbits. The point is that a simple rule about how the present depends on the recent past can generate the Fibonacci sequence naturally as a model of cumulative growth. So the sequence belongs to a bigger family of ideas in science and math, ideas about recursion, feedback, and systems that build themselves step by step, where what comes next is shaped by what came just before. Now, if you imagine this as a bedtime story, you can picture Fibonacci as a quiet staircase built from two initial steps and then rising by repeating the same gentle motion again and again. And what makes it relaxing is that nothing about it is sudden. It's predictable without being boring. It's orderly without being rigid. It grows the way many natural processes grow, not in sharp jumps, but in smooth accumulation. And from here, we can drift into the golden angle more directly, because it's the golden angle that turns Fibonacci from a list into a visible pattern, especially in plants, where spacing matters and shadow matters and packing matters. And the most comforting part is that we don't need heavy math to understand it. We only need a simple intuition. If you keep placing new growth at an angle that never lines up into repeating rows, the placements spread out evenly, filling the available space with minimal waste. And when the angle relates to F, that even spreading becomes remarkably consistent, producing those spiral families whose counts often land near Fibonacci numbers, like a quiet fingerprint left by efficient growth. The golden angle is one of those ideas that sounds mysterious at first, but becomes very gentle once you let it settle. It's simply the angle you get when you divide a full circle in a way that relates to the golden ratio, which comes out to about 137.5 degrees. And what makes this angle special is not that it's magical, but that it's stubborn. It doesn't line up nicely with itself. If you keep rotating by this angle over and over, you never land on the same direction again in a neat, repeating pattern. This quality turns out to be incredibly useful for living things that grow by adding new parts one at a time. In plants, especially, growth happens at the tip. New leaves, buds, or seeds are added sequentially, and where each new one appears depends partly on where the previous ones already are. If a plant were to place each new leaf directly above the last, the leaves would stack and shade one another. If it used a simple fraction of a circle like a quarter turn or a third, the leaves would line up into rows, again creating overlap. But when the angle is close to the golden angle, something different happens. Each new leaf appears in the largest available gap between older leaves, spreading growth evenly around the stem over time. This pattern is called spiral phyllotaxis, and it's one of the clearest places where Fibonacci quietly enters the physical world, not as a command, but as a consequence of even spacing. When you look at a stem from above, the leaves trace spirals upward, sometimes clockwise, sometimes counterclockwise, and when you count these spiral paths, you often find Fibonacci numbers emerging as the most stable counts. These spiral paths are called parasticides, and they aren't drawn deliberately by the plant. They appear naturally when points are placed one by one at a nearly irrational angle around a growing axis. It's calming to imagine this process unfolding slowly. A plant doesn't calculate, it grows. And as it grows, simple local rules about space and avoidance give rise to global order, an order we later recognize as Fibonacci. Now, this same logic extends beyond leaves into flowers, where growth points are packed tightly together in expanding patterns. When a flower head grows like a sunflower, new seeds are added near the center and pushed outward as more arrive. If each seed were placed at a simple angle, clumping would occur. But with a golden angle-like placement, seeds settle into gaps and the structure self-organizes into those familiar double spirals. The fascinating part is that the plant doesn't need to know how many spirals it will end up with. The number of visible spirals depends on the size of the flower and how many seeds are packed in. But the most stable spiral counts tend to be Fibonacci pairs because those pairs best approximate the golden ratio at different scales. As the structure grows larger, the system naturally shifts from one Fibonacci pair to the next, like moving up a ladder of increasingly accurate approximations. This gives the impression that Fibonacci is being followed deliberately, when in reality it's being approached gradually through growth and geometry working together. And if that feels subtle, that's because it is. This is one of the quiet themes of tonight's journey. Fibonacci in nature is not loud. It doesn't announce itself with exactness. It emerges softly through repetition, through spacing, through the patient unfolding of form. Now let's take this same idea underground, where roots grow not toward light, but toward water, nutrients, and stability. Root systems often show spiraling and branching patterns as they navigate soil, which is an uneven, resistant environment. Soil is full of obstacles, compacted layers, stones, and pockets of varying moisture. A straight path is rarely the best one. Spiral and curved growth allows roots to probe space efficiently, covering more volume without retracing the same paths again and again. This spiral tendency can help roots penetrate dense soil, distributing pressure and reducing resistance, much like a screw entering wood. And while root spirals aren't neat Fibonacci diagrams, they reflect the same preference for distributed exploration, for patterns that balance expansion with efficiency. It's another example of how growth under constraint tends to favor curved, spreading paths over rigid lines. Above ground, branches often echo similar principles. Branching angles and spacing help distribute weight, resist wind, and optimize access to light. When branches emerge in staggered or spiral arrangements, they avoid competing directly with one another, reducing mechanical stress and shading. These arrangements are flexible, not exact, but they often hover near Fibonacci-related proportions because those proportions help distribute forces evenly through the structure of the plant. It's not that Fibonacci guarantees strength, it's that systems shaped by evolution often settle near patterns that work well, and Fibonacci is one of the most stable neighborhoods for such patterns. Now, it's important to pause gently here and clear a common misunderstanding. Fibonacci numbers are not laws of nature in the way gravity is. They are not instructions etched into DNA telling plants how to grow. They are descriptive tools, patterns we recognize after the fact, because they show up frequently when growth is sequential, space is limited, and efficiency matters. Nature doesn't follow Fibonacci because Fibonacci is special. We discovered Fibonacci because it describes something nature often does. And this distinction matters because it keeps the story grounded and calm rather than mystical. Fibonacci is a lens, not a spell. And when we use that lens carefully, it reveals something very soothing about the world. that complex beauty can arise from simple rules, that order can emerge without planning, that growth can be both flexible and structured at the same time. From here, we can widen the view again, stepping away from plants and into the broader idea of self-similarity, because Fibonacci is closely related to fractals, patterns that repeat across scales. In fractal systems, a small part resembles the whole. Branches resemble trees. Rivers resemble watersheds. Blood vessels resemble entire circulatory systems. These patterns aren't exact copies, but they echo themselves again and again at different sizes. This repetition allows efficient distribution, whether it's water, nutrients, energy, or information. And Fibonacci often appears in these contexts because recursive growth naturally produces sequences where the present builds on the recent past, the same structural idea behind the Fibonacci rule. In ecosystems, fractal and spiral patterns create layered habitats, offering many niches within a small space. Coral reefs, for example, have branching structures that provide hiding places, feeding grounds, and flow paths for water all at once. This complexity supports biodiversity by reducing direct competition, allowing many species to coexist by occupying slightly different spaces and roles. And while coral growth is influenced by chemistry, light, and water movement, the resulting forms often resemble branching and spiraling geometries that feel familiar again and again across the natural world. It's as if life keeps rediscovering the same comfortable shapes for solving similar problems. And now, as this idea settles, you might notice something important. The Fibonacci sequence is not only about growth outward, it's also about balance between what has been and what is coming next. Each number carries memory. It contains the two previous steps inside it. In that sense, Fibonacci is a mathematical story about continuity, about how the present is shaped by the immediate past, not by a distant plan, and that makes it a surprisingly gentle idea to fall asleep with, because it mirrors how thoughts often work when we relax. One thought leads to the next, influenced by what came just before, slowly drifting rather than jumping. From here, we can move softly into how Fibonacci appears in animals, in horns, shells, and body forms, not as decoration, but as a way to manage growth, stress, and proportion over time. When we turn our attention from plants to animals, Fibonacci patterns continue to appear, not as strict formulas, but as gentle guides for growth and form. One of the clearest examples is found in shells, especially those of mollusks. As these animals grow, they add new material to the edge of their shell, expanding it outward without changing its overall shape. This kind of growth is called self-similar growth, meaning the form remains consistent even as size increases. The curve that results is often a logarithmic spiral, closely related to Fibonacci ratios. This spiral allows the shell to grow larger without becoming fragile or awkwardly shaped, maintaining strength and balance as the animal matures. It's a quiet solution to a practical problem: how to grow continuously without rebuilding from scratch. And because this solution works so well, evolution has returned to it again and again across many species and environments. Horns and tusks follow similar principles. The spiraled horns of animals like rams distribute mechanical stress along the curve, reducing the chance of fracture during impact or combat. The spiral shape allows the horn to grow longer without becoming too heavy or unstable, balancing strength with efficiency. This is not an artistic choice. It's an engineering one, arrived at slowly through survival and adaptation. In each case, Fibonacci-like spirals help manage tension, growth, and proportion over time. Now consider spider webs, another quiet example of spiral logic. A web combines radial lines with a spiraling thread that moves outward from the center. This design maximizes the area available to catch prey while using minimal material. The spiral spacing adjusts dynamically as the web grows, keeping distances functional rather than perfectly uniform. The spider is not calculating Fibonacci numbers, yet the resulting structure often resembles mathematical spirals because those shapes solve the same problem the spider faces: how to build something strong, flexible, and efficient with limited resources. And so the pattern appears again, not because it is followed, but because it works. At much larger scales, the same geometry appears in weather systems. Hurricanes and cyclones spiral because rotating fluids under specific forces naturally organize that way. The Coriolis effect, pressure gradients, and conservation of angular momentum shape these massive storms into curved bands that echo logarithmic spirals. These spirals help distribute energy efficiently, allowing storms to sustain themselves over long distances and time periods. Though not exact Fibonacci spirals, their resemblance reminds us that similar physical constraints often lead to similar shapes, whether the system is biological or atmospheric. This repetition across scales is deeply calming. It suggests that the universe favors certain solutions, returning to them gently whenever conditions align. And this brings us to an important idea. Fibonacci patterns are not isolated. They are part of a broader family of natural order that includes fractals, spirals, waves, and branching networks. These patterns emerge when systems grow incrementally, respond locally, and adapt continuously. They are signs of processes unfolding over time rather than plans imposed from above. In this sense, Fibonacci becomes less about numbers and more about rhythm, about how change accumulates, about how complexity grows from simplicity. If we slow down enough, we can begin to see Fibonacci not as something hidden, but as something patient, quietly revealing itself through repetition. Now let's return gently to plants, but from a different angle, looking not at structure, but at efficiency. One of the reasons spiral arrangements are so common is that they reduce competition. Leaves arranged in spiral phyllotaxis avoid shading one another. Seeds packed in spiral patterns avoid gaps and overcrowding. Branches staggered around a stem distribute weight and wind stress more evenly. This efficiency is not about perfection, it's about resilience. In real environments, conditions change. Light shifts. Wind varies. Water availability fluctuates. Patterns that allow flexibility tend to survive, and Fibonacci-like arrangements provide just enough order without becoming rigid. This balance between order and adaptability may be one of the deepest reasons these patterns persist. They are forgiving. They allow small errors without collapsing the whole structure. And now, as we move further into this idea, it becomes clear why Fibonacci has captured human attention for centuries. Not because it is mysterious in a mystical sense, but because it mirrors how we experience the world. Patterns that are neither chaotic nor overly predictable feel comfortable to the mind. They hold interest without demanding effort. This may be why Fibonacci-related proportions often feel calming to look at, whether in nature, art, or architecture. The eye moves easily along a spiral. It doesn't get stuck. It doesn't feel overwhelmed. This visual flow translates into a mental one. And so artists and builders have long drawn inspiration from these patterns, sometimes consciously, sometimes intuitively. From ancient temples to Renaissance paintings to modern design, proportions close to the golden ratio have been used to create balance and harmony. These choices don't force attention. They guide it gently. The same way this story does, moving forward without sharp turns or sudden jumps. And here, it's worth noting something important. Humans didn't invent these patterns, we recognize them. We noticed that certain shapes felt right long before we could explain why. That recognition came from living within nature, from being surrounded by branching trees, spiraling shells, flowing rivers, and curved horizons. Our sense of beauty was shaped by the same world that produced Fibonacci patterns in the first place. In that way, our appreciation of these proportions is less surprising. It's familiar, it's a memory of forms we've always known. And as this realization settles, the Fibonacci sequence begins to feel less like a mathematical object and more like a quiet companion. A simple rule that echoes across life, growth, and perception, not demanding attention, not insisting on understanding, just present, repeating softly, like a heartbeat or a breath. From here, we can drift gently into the more reflective side of this story, the philosophical space where science meets wonder, and where the idea of pattern becomes a way to rest the mind rather than stimulate it. As we move deeper into this quiet reflection, it helps to let go of the idea that Fibonacci is something to be solved. Instead, we can think of it as something to notice. A rhythm that repeats not because it must, but because it fits. In nature, growth rarely happens all at once. It happens step by step, addition layered on addition, each change building gently on what came before. This incremental growth is where Fibonacci naturally appears, not as a rule imposed from outside, but as a consequence of growing forward without undoing the past. When a plant adds a new leaf, it doesn't rearrange the old ones. When a shell grows, it doesn't rebuild its earlier chambers. When a pine cone forms, each new scale finds the next available space. This simple principle, always adding, never replacing, creates patterns that feel inevitable, even though they are never perfectly exact. And this imperfection is important. Nature doesn't chase mathematical purity. It favors patterns that work well enough across changing conditions. That's why Fibonacci patterns in living things are always approximations. Close enough to be efficient, close enough to be stable, flexible enough to adapt. This balance between consistency and variation is one of the most calming ideas in all of science. It suggests that life doesn't need precision to thrive. It needs direction, feedback, and time. When we think about time in this way, Fibonacci becomes a story about patience, about how complexity doesn't arrive suddenly but unfolds slowly, one small addition at a time. This is true in biology, in ecosystems, and even in our own lives. Most meaningful change happens gradually, often unnoticed in the moment, only visible when we look back and see how far the spiral has carried us. And this perspective begins to soften the mind. Because if growth is incremental, then rest is not a failure. It's part of the rhythm. In nature, there are pauses, seasons where growth slows, seeds that wait, dormant buds that hold their shape through winter. Fibonacci patterns don't rush. They emerge over time, shaped by conditions, responding gently to what is available. In this way, they mirror the natural cycles of activity and rest, effort and recovery. Now let's turn our attention inward to how the human mind responds to these patterns. When people look at spirals, branching forms, or balanced proportions, the brain often shows signs of ease. The eyes move smoothly. The attention doesn't snag or strain. There is enough structure to follow, but enough variation to remain interesting. This balance is thought to be deeply soothing. It engages the brain's pattern recognition systems without overwhelming them. This may be why natural environments feel restorative. Walking through a forest, watching waves roll in, or tracing the curve of a shell can lower stress and quiet mental noise. These environments are rich in patterns that echo Fibonacci-like organization. Branches split gradually. Paths curve rather than stop abruptly. Views open slowly instead of all at once. The mind relaxes because it doesn't have to defend itself against chaos or monotony. It can simply follow. And when the mind follows gently, sleep becomes easier. This is one reason why Fibonacci patterns and natural geometry appear so often in calming art, architecture, and meditation spaces. They don't demand attention, they invite it softly, and once attention settles, it can drift. This brings us to an important distinction. Fibonacci is not special because it is magical. It is special because it reflects how systems grow when they are allowed to develop organically without force, without haste. In that sense, it represents a kind of trust. Trust that small steps accumulate. Trust that order can emerge without control. Trust that complexity doesn't need to be rushed. And this trust is something the body understands deeply. Your breath follows a rhythm that builds on the last breath. Your heartbeat adds one pulse after another, never starting over, always continuing. Your thoughts arise in sequence, each one shaped by what came before. Fibonacci is not foreign to you, it is familiar. It lives quietly in the way time passes and the way rest arrives. As the story continues, it's perfectly fine if details begin to blur. You don't need to hold on to definitions or examples. The patterns themselves don't need to be remembered consciously. They work even when unnoticed, the way tides respond to the moon without needing awareness. You can imagine the Fibonacci sequence now as a soft spiral, widening slowly, not pulling you forward, but allowing you to settle into its curve. There is no end point you need to reach, no conclusion to arrive at, just a sense of gentle unfolding. As we come gently toward the end of this journey, there's nothing left to explain and nothing left to hold on to. The Fibonacci sequence does not ask for understanding in the way a problem does. It asks only to be noticed and then quietly released. Like so many patterns in nature, its meaning does not come from a final answer, but from the feeling it leaves behind. A sense that growth can be calm, that order can arise without force, that beauty does not need urgency. You can imagine now that the spiral has slowed. It no longer expands, it simply rests wide and open, holding space rather than moving through it. The numbers fade, the shapes soften. What remains is the rhythm beneath them, the steady addition, the gentle continuation, the quiet assurance that each moment builds naturally on the one before. Nature does not rush toward completion. A shell grows at its own pace, a leaf unfolds when it is ready. A branch extends only as far as it can be supported. And in the same way, rest arrives when it is allowed. Sleep is not something to reach. It is something to drift into, gradually, without effort. If your thoughts are still present, that's okay. They can settle on the spiral, tracing it once, then losing interest, the way the eye eventually stops following a curve and simply relaxes. You don't need to push them away. They will slow on their own, following the same quiet rules that shape everything else. Somewhere in the world right now, leaves are arranging themselves around stems. Seeds are packing into cones, shells are growing chamber by chamber, stars are moving in wide arcs through space, all of it unfolding according to simple principles, guided by time and balance rather than speed. And you are part of that same unfolding. Your breath already knows the pattern, in and out, one following the other. Nothing skipped, nothing forced. Your body knows how to rest just as deeply as nature knows how to grow. There is no instruction required. As the night continues, you can let go completely. There is no more story to follow, no more ideas to hold. The quiet language of patterns can fade into the background, doing what it has always done, shaping the world without needing attention. If sleep comes now, let it. If it comes later, that's fine too. The spiral does not judge timing. It simply continues patiently, endlessly, softly. For now, you can rest in the comfort of knowing that beneath complexity, there is rhythm. Beneath motion, there is balance. And beneath all the thinking, there is a natural ease waiting for you to allow it. Sleep well. Let the pattern carry you gently through the night.